But again, since the statements of this proof were all given to you, you have to follow their train of thought. Because maybe some of you really like alternate exterior angles, and so you're just like, well, I want to show that angle 1 is congruent to angle 8, and if that's true, I know lines are parallel. Well, that's a reasonable way of showing lines are parallel, but that may not be what they're going after. So since we're given all the statements and we don't have free range of proving this our own unique way, we have to look at, okay, where are they going? And so, of course, they're going to start off with that these angles are supplementary, but they're going to work down towards, and they're going to work down to showing that angle 1 is congruent to angle 5. So they're going to use, if corresponding angles are congruent, then lines are parallel. That's their route of going about it. So we need to follow that. We need to be able to justify all of their reasons. So, what they're going to use, again, is linear pair. We know right now that angle 1 and angle 7 are supplementary. So what they're going to do is prove that angle 1 is congruent to angle 5 because angle 5 and 7 are also supplementary. So they're using linear pair. You could use vertical angles. There's lots of ways you could went about this, but we're going to have to follow their train of thought. So we're going to show that since 1 and 7 are supplementary and 5 and 7 are supplementary, then 1 and 5 have to be supplementary. There's actually a theorem out there, and it's called the congruence supplements theorem. And it states that if two angles are supplementary to the same, they have to be congruent. So if two angles, 1 and 5, if two angles are supplementary to the same angle, angle 7, then those two angles, 1 and 5, they have to be congruent. That's called the congruent supplements theorem. But they just kind of drag it out. So we'll go with their train of thought. We're always going to start with our given. So that angle 1's congruent. Angle 1 and 7 are supplementary. From there, it would make logical sense that if we said that the objects are supplementary, let's go ahead and transition into their measurements and equality. Let's make that transition. So what justifies step 2? Definition of supplementary. After that, we state that angle 5 and angle 7 are supplementary. So this is kind of, again, one of those times where like a statement is just kind of out of left field, just random. Okay, when that happens, look at your givens. Maybe that statement was given to you. If not, take a look at your diagram. And in this case, how do I know those two angles are supplementary?
Definition of linear pair.
Definition of linear pair. Good. From there, again, if two angles are supplementary, then why do their measures equal to 180 degrees? Definition of supplementary. Then after that, now I'm stating that the measure of angle 5 plus the measure of angle 7 equals the measure of angle 1 plus the measure of angle 7. How do I know that? Well, what are they doing?
Substitution.
It is substitution. Okay? It's substitution property. Now, if you had written transitive property of equality, I can see your train of thought. I understand where you're getting that, but I prefer substitution property of equality. Okay? Because what's happening is they have this sum here, the sum of measure of angle 5 plus the measure of angle 7. It's also right there. Then they have this other sum that they're setting it equal to, the measure of angle 1 plus the measure of angle 7, which is also up here. Well, these two sums equal the same thing. They equal 180 degrees. What they're doing is they're replacing this 180 degrees. So they've got the blue sum. Well, actually, I guess they're starting with here. They're stating that the measure of angle 5 plus measure of angle 7 is equal to, well, in the place of 180, they have replaced it with what 180 also equals to, and that is this other sum. So I would prefer that you're saying substitution. They're plugging in the measure of angle 1 plus the measure of angle 7 in place of 180, but I can also see transitive property of equality. So I'm going to write definition of, sorry, I just read that, substitution property. That's what I prefer you guys write, but I can also see transitive property of equality. From there, if I know that this sum equals that sum, then how do I all of a sudden get to the measure of angle 1 equals the measure of angle 5? Subtraction property of equality. So what they're doing is they're subtracting the measure of angle 7 from both sides. Remember that that's just a big, ugly variable. That the measure of angle 7, all of that notation, is representing some number, like 17 degrees or 88 degrees. It's representing some number. And you can subtract the same number from both sides of the equation, and that is justified by the subtraction property of equality. You must put of equality on that one. Yes, sir?
Shouldn't there be a 6.5 because they use symmetric property?
There should be. You're absolutely correct. Because the measure of angle 5 is on the left, that should stay on the left. You can't do 2 steps in one. You can't subtract a value from both sides and change what's on the left and the right. So yes, that is correct. There should be a step before this. Or they should have just not switched them. Should have just not switched them. Because they didn't need to switch them at all. Good. And then so if I know that 2 measures are equal, then why are the objects the same size, same shape? Definition of congruent angles. So, again, you will never use the definition of congruence. We're not going to use that. We will use definition of congruent angles or the definition of congruent segments, one of those two. And that's what allows you to go from measurements to objects, or lengths to objects. And then if I know that if I know that these 2 angles, angle 1 and angle 5, look at our diagram. What's the relationship, or what's the classification of angle 5 and angle 1? Corresponding. So make sure that your reason matches your logic. So I started off knowing, before I stated this, I did all of this work just to show that angle 1 and angle 5 are congruent. And they happen to be corresponding angles in that diagram. So if corresponding angles are congruent, if I know that, then I can conclude that lines are parallel. So that's the conclusion of my if-then statement. Questions about these 2 proofs? I'm really hoping these were pretty easy for y'all, especially that you didn't have to come up with the order of the statements. You're just justifying things. But we're going to have to get to the point where we can start and finish a proof on our own. Okay, cool. Well, then let's flip that piece of paper over, and let's look at those notes. Do a little bit of review. So on the other side, you got Activity 8's notes. In last class, we should have filled out the first 2 blanks, correct? Yes. Wonderful. Now again, I'm hoping that Activity 8 is a review. It should be a review of Algebra 1 for all of us. The first part is talking about slope, and there's lots of ways that you and I know how to find the slope of a line. We could be given 2 points that are on that line, and so we can plug those x and y values into the slope into the slope formula. Sometimes we'll be given the equation of a line, and we can identify the slope of that line just based off of the equation. Because once it's in slope-intercept form, the slope is just the coefficient of the x term once you have it in slope-intercept form. If it starts off in standard form, you got to do a little manipulation to that equation. Then you have to solve for y, so that you have y equals mx plus b. If it's graph, then we can just count, what's my rise over run? We can get the slope that way. So we got a lot of ways of figuring out the slope, and that was Activity 8, Part 1. And then Part 2, which we're really going to focus on today, is writing the equations of those lines. And whenever you write the equation of a line, you need to know at least 2 things. There's 2 things you must know. You have to know at least one point that line's going to pass through or go through. You got to know at least one point that line passes through. Then once you have that, and that could be your y-intercept, that could be your x-intercept, that could be just any random point, but you have to know at least one point that the line goes through. And then you need to know something about your slope. And I'm being purposefully vague about that. Because you can either determine what your slope is by giving, like if you're given 2 coordinate points, you can use the slope formula. Or maybe they give you a description of this slope. Like it has to be parallel to this line, or it's got to be perpendicular to this line. But you have to know something about your slope. And once you have those 2 things, then we're going to plug it into the point slope formula. So that's going to be our focus today. But before we get there, let's just review this stuff. I gave you examples of what these equations would look like, and I also gave you what these lines graphically would look like. I think we're all comfortable with negative and positive slopes. Okay, so here's an example of an equation with a negative slope. Since it's in slope-intercept form, we can easily identify what that slope is. So for that first one, what's the slope of that line? -5/12. We can see that, very easy. However, can we just look really quick at this equation and quickly identify what the slope is? No, okay, because this is currently, well, kind of. It's kind of in a standard form. It's definitely not slope-intercept form. But it's not as easy. Some of us can do it in our head a little bit quickly, but it's not just instantaneously look at the equation and boom, we all can tell. But some of us can do it in our head and say, okay, plus 9x divided by 3, so my slope is +3. Some of us can do that in our head. But you need to put that equation in slope-intercept form. Then you can quickly identify the slope. The 2 we need to focus about is the 2 outliers, I guess, is when you have a slope of 0. Keep your z's together. When you have a line that has a slope of 0, it's going to be horizontal. Slope of 0 is horizontal. That's what it's going to look like graphically. So I gave you line N as an example of a line with a slope of 0. And then the one that would be perpendicular to that is if the slope is undefined, and that's when it's vertical. Also, refresher course of when you have your undefined and your slope of 0, the equations look a little different. So you've got, if it's horizontal, it's y equals some constant, y equals some value. When it's vertical, it is x equals some constant. So, believe it or not, this is in slope-intercept form, in all honesty. This is an equation of a line that has a slope of 0 that passes through, its y-intercept is +9. So if this is my graph, then this line is going, y equals 9 is going to pass through, be perfectly horizontal with a slope of 0, and this would be at 0, 9. That's what it would look like. But this is kind of in slope-intercept form, the whole y equals mx plus b, because my slope is 0, and my y-intercept is +9. But we're not going to waste our time writing 0 times x plus 9. We're not going to waste our time writing all that, because we know 0 times anything is what? It's just 0. And then 0 plus 9 is just 9. Because equals 9, that's pretty much in slope-intercept form. We just don't waste our time with that nonsense. So you need to know that the slope is 0. Then when you have an undefined line, a slope that has a line that has the slope of undefined, that's going to be x equals some value. So like if I wanted to graph x is equal to -2, that means it's going to be over here at -2, 0. That's where it'll intersect that x-axis. But every single point on this line has an x-coordinate of -2. So no matter what, x is -2 anywhere on that line. Same thing here with y equals 9. Any point on that line, no matter where you stop, any point on that line, the y value is going to be